In this problem, we're trying to find the average distance from the center of a ball to all the points within that sphere, and the max radius is going to be A. And we can kind of draw this out a little bit. Here's the sphere, it's the radius of A. Now it's got a ton of points inside of it, like so many points that it actually makes a volume out of that, right? And what we can do to find the total distance is we can multiply like this distance, and then add that distance, and that distance, and that distance, and add up all the little distances in here. And some of those distances are going to be really small because they're going to be close, and some of the distances are going to be really far because they're over here. So we can take all the distance, and multiply it by the volume in order to get the total distance. But you see, here's the problem. The distances that we do, some of them might be really, really small. And if we did that, then we'd get too small. If we did small throughout the entire distances, like for all of them, we use the really small value, we would get very, very, very small volumes. So that wouldn't be good enough. If we did the max distances, like all the distances out here, and multiplied by that, all the little volume points, that'd be too much volume. So what we need to do is we need to multiply this by the average distance. When you multiply the average distance by the volume, you'll get the total distance. Okay, so you need to get the average distance right in between so that every single point have the same distance. You multiply that by all the volume points and you'll get the total distance. So let's reverse engineer this. Let's divide the total distance by volume and we will be left with the average distance. So we're going to need to do that. Now, in order to find the total distance, what we're going to do is we're going to take, we're basically going to multiply the radius like we did over here. The distances are going to be R, okay, and then we're going to multiply it by the volume. So in order to get the volume, that would be dV. And this R is supposed to represent average distance, of course. So we're going to get R and then times the integral of the dV, that's going to be the volume. And then we're going to divide this by the volume. And so these things should essentially cancel out and we'll be left with the average distance, okay? Again, so average distance times volume, that's going to be distance times volume divided by the volume. Let's try to figure out what dV is for this sphere. I put a triple integral, but it may not be that. But let's start with the volume. That's going to be 4/3 pi r to the third. And if we dV that, then we'll actually get 4 pi r squared dr. So we only have one integration here. We're going to go 4 pi r squared dr. We've got the r on the outside. And let's figure out where the limits of the r's are. Obviously, it's going to be 0 to the max is going to be a. So we'll put that in there. And we should be able to integrate this pretty easily. This is obviously going to go on the inside over here instead of being on the outside. So this is going to be r to the 4th divided by 4. We've got the 4 over there. So those things will cancel out. We're still got the pi inside. This is going to go from 0 to a. So we're basically left with pi to pi and then a to the 4th. And that's going to be the solution to the top part. But we'll divide this by the volume, and what isn't the volume just going to be 4/3 pi a squared, a to the 3rd? So let's divide it by 4/3 pi a to the 3rd. If we do that, we'll get a 3 on top, 4 on the bottom, pi a to the 3rd, and this will simplify down to be 3/4 a. And there we go. That's the answer.